Alright, welcome back to Particle Physics and the Standard Model. This is lecture 29. And last time we saw the fundamental importance of gauge invariance in constructing particle physics theories, correct? Until that point we had taken Lorentz invariance very seriously because we needed causality and locality and these concepts. But now we also want invariance under redundancy in the descriptions of fields such as this, right. Why is it so fundamental is not completely clear. Nevertheless, nature seems to have chosen to put this symmetry in whenever we want to construct a local field theory, and we follow this program and find that it gives rise to amazing results that match with experimental observations, right. So we saw how to construct a gauge invariant theory for complex scalars and for spinors, right. So these went under the name of scalar QED and spinor QED, which have real world applications. If you think of this as gauge invariance that comes in electromagnetism, right. It's the same gauge invariance that we saw in Maxwell's equations, but now we are seeing it in a more Lorentz covariant or Lorentz invariant way. Agreed? And in that process we saw the concept of a covariant derivative, right, where the derivative itself redefined this way, where we put in the force carrier, the photon in this case, as part of the entire derivative that you put into the kinetic term. The derivative itself transforms like a field under gauges, correct. And we also saw how the photon actually transforms under gauge invariance, and all of this put together gives us a nice complete invariant theory, right. And from that we went on to another level of understanding this whole business, which is that if you wanted a local field theory with local phase invariances, right, under invariance under a rephasing of fields, then you can't help having a gauge boson, which is what we call a force carrier, mediator, etc., right. So this is where we get the concept of there being a force carrier associated with every fundamental force. Okay. Now let us take this one step further in this lecture, okay, to get closer to the actual standard model. All right. What we've seen thus far as QED, right, corresponded to gauge invariance under an abelian group. What is that group? We saw this in the very first lectures. That's nothing but U1, unitary group of one dimension. This is exactly why we were able to do simple refacings of the field and call them the gauge transformations, correct. To distinguish this U1 from other U1s, I like to put the subscript EM, okay, just to avoid all confusions, right. But of course we saw when we introduced group theory that there are also non-abelian groups, right. So it's natural to wonder whether there are field theories that describe interactions in nature that also make use of non-abelian group gauge invariances, okay. And it turns out that is indeed the case for the weak interactions and the strong interactions, okay. So in physics, when you apply a non-abelian group and that is a symmetry of the theory, we call that Yang-Mills theories, okay. The reason they get their own name, it's not a very trivial thing. When you have non-abelian groups, there are lots of problems that you would run into, and this is what held people back historically from exploring non-abelian groups. They knew there were non-abelian groups, They already had discovered QED, but Yang-Mills comes with its own set of physical problems, and we'll see some of them along the way. Okay. So how do Yang-Mills theories work? It's the simplest generalization of a transformation like this. Okay. All I'm going to do now is, instead of writing it as a phase, as long as my fundamental field is invariant under a transformation like this, okay, where it doesn't always have to be the case, but then we're dealing with complex fields, so might as well call this a complex matrix. In fact, it is a unitary matrix. Okay. As long as the theory is invariant under this transformation, and if the unitary matrix has more than one dimension, you have a non-abelian theory. Okay, you have a Yang-Mills theory basically. All right. Now, I can characterize a unitary matrix this way. Okay, I can parameterize it this way. I can write it in terms of the generators. Agreed? I'm going to call the generators tau A. We saw this, right? In Lie groups, you can populate the entire group using the generators. This is exactly what we did last time when we did Lie groups. Correct? So the tau A's are the generators of the particular group that we are thinking about. For example, what is it for SU2? It's the Pauli matrices, correct? With the factor of half. So SU2, the group that we see everywhere. Never forget, whenever you are stuck with these things, always go back to SU2. Okay. And what are the alphas? The alphas are just real coefficients. Okay. All the complexity, all the complex numberness is in the I in front. All right. And notice that for every generator, I am giving it its own alpha. That's why the label A. Okay. A basically counts the number of generators that we have for the group. Okay. So, of course, you see that if I have a unitary transformation like this, then any inner product that I take, imagine the state that I get out of this, right? Let me write it in a different color. Imagine that the states that I get out of these fields are, phi, psi and chi and so on. If I have unitary transformations, then the inner product is preserved. Correct? So preserves, of course, this is a complex because it's at the amplitude level, complex inner product. Okay, this is the reason why we think a lot about unitary groups in particular. Okay, in principle, you could have any sort of group under which these matrices transform, but for gauge theories, we think of unitary groups in particular because we want to preserve the inner product. Okay, excellent. Now, we know how the, we know there is an algebra for the generators. We already saw this, correct, when we talked about spinors and so on. So, we know that there is an algebra for the Pauli matrices. In other words, there is a commutation relation for the Pauli matrices, correct? In general, okay, you can write an algebra for the generators. Okay, so you can always have an I in front, but notice that to get the indices right, I do need another tensor like object in front. I'm just going to call it F because that's the conventional notation for that. All right. So what is F for? Let me write it in red again. For example, for SU2, what is the F here? The FABC is nothing but the Levi-Civita tensor, right? But similarly for any group, for any Lie group, you will have a unique F, okay, and this F, we can give it a name. The FABC is called the structure constant. The structure constant uniquely determines the group that we are talking about, okay. All right, so we'll see one other example of a structure constant as we go along the way. For SU3 we will see, okay. Okay, by the way, what is FABC for abelian groups? Obviously the structure constant is 0, right? There is no real generator to talk about, right? So you know the generator is just unity and the commutator vanishes for that, correct? Okay. So we are now ready to construct our first gauge invariant theory under a Yang-Mills gauge, okay. So Yang-Mills gauge invariant theory. So what is the first term I would write down? It's the kinetic term, correct? And as before, I am going to use a covariant derivative, okay, and contract the indices correctly. Agreed? And naturally I have started using complex scalars, right, because we are talking about unitary groups already, right, unitary transformations. Okay, now you should remember now that since we are talking about matrices, the phi field I have written down is also represented by a matrix, okay, it is no longer just a complex scalar, okay, so it is worth writing down. This is also, think of it as a column matrix, okay, the phi, because we need to transform it under a square matrix, right? Okay, good. What else? That is the kinetic term. What about the kinetic term? This is the kinetic term of the phi field. What about the kinetic term of the associated gauge boson field? Okay, let me just call it A if you want, okay, and then in fact I am going to label the A's with a small a, we will see why. This is also called the Yang-Mills Lagrangian, okay. How about that? This would also look very similar to how we have been writing the QED Lagrangian, the free photon Lagrangian, except with a little more, with a little bit of twist. You see what I have done here? I have put that A index, we saw this A index over here, right, that labeled the generators, right, over here. I have put that in because there is, for every A there is a field strength tensor on its own, okay, and again here I have used Einstein summation convention, so that repeated indices are summed over. So the A's are summed over here, okay. So what is this F mu nu? The F mu nu, okay, this is the most important thing now, is this you must be familiar with. The first two terms, okay, let's go back. The first two terms you are familiar with, right, from QED, but the most important is this term. Okay, just like that I have introduced in the field strength tensor itself something like an interaction between to gauge boson fields, right? Notice that this term goes to 0 for abelian theories, right? This is just what we saw in QED, correct? So where did this come from? That came from constructing the field strength tensor in terms of the covariant derivatives themselves. Okay. And what is F mu nu here? That is just F mu nu A for each of the A's, and then I am multiplying those with the corresponding generators and then summing them over. Again, Einstein summation is being used here. Okay. So this here is the more fundamental definition of what a field strength tensor is. Okay. Now go back and convince yourself that for QED, when we wrote down just the first two terms, right? This commutator of the covariant derivatives is exactly what the first two terms were. Okay. So I have not yet written down the covariant derivative, but it should be obvious at this point, right? The covariant derivative here for non-abelian cases is, it looks exactly the same as before, except I wouldn't just put an A mu, I would also once again contract the indices of the generators. Okay, good. See, when you go do this, right, when you use the covariant derivative, put it into the commutator now, you will end up with this. It's not very easy to see, but go check this. Okay, it's actually kind of easy to see once you know the commutation relation of the generators. Okay, so what is not very easy to see is that this term is gauge invariant. This term, right? It is indeed gauge invariant. And this you can check for yourself. This is not very trivial, but go do this. Okay, see for yourself that this is indeed a gauge invariant term under the gauge transformations that we just written down. Okay, so that's a homework problem for you. So let me just give you a hint. To see that, you need to make use of the Jacobi identity. That's the hint. Okay, go look up what the Jacobi identity is if you've forgotten. It's a relation between commutators. It's an associative relation between commutators. Okay, good. So you can also do this for just infinitesimal transformations. Okay, that should be good enough. All right. So I've told you the field strength tensor, I've told you the covariant derivative. How do the fields themselves transform? That also is not hard to see. Okay. Since I've written the covariant derivative, well, don't worry about that. So we've already written this down in a different form. We just wrote u of x. I'm just going to write this in this new parameterization. So this is how the scalar field in this case transforms. But what about the gauge boson? The gauge boson transforms like this. Okay, partial mu alpha a of x. If I had stopped here, that would still look like an abelian theory, right? But something more happens in a Yang-Mills theory, and you guessed it, the structure constant enters obviously, and then I have the same alpha but with a different index, and the field. Okay, notice how non-trivial this is, right? So the Lorentz index is carried 2 times by the field and once by the derivative. Earlier we saw it was carried once by the field and once by the derivative, right? But when the second time it appears, it actually picks up the gauge. Alpha is the gauge, right, which helps you to describe the field in a different way. And of course, it also comes with the the structure constant. Correct? Notice 1 or 2 things here. Okay, I've been writing down the index A for the gauge field, right, for the gauge boson. Correct? But I've also been writing it down for the generator itself. Correct? In other words, what I'm implying here is that the number of gauge bosons in this theory is the number of generators in the theory. You agree? That's the only way I can contract the A's. Right? Notice also that this is a simple transformation of the fields under the gauge, whereas this is a much more non-trivial transformation. Correct? Said in group theory language, the phi's live in the fundamental representation. Remember fundamental? In group theory language, the matrix, when you represent the group, the matrix group by the matrices themselves, that's a fundamental representation, right? That's, I mean, it's so fundamental we don't even think about it, right? It's exactly what this is. You put in the matrix itself, and of course the phi's also live in the fundamental representation because they are the ones that are undergoing the transformation. So they are the group elements also. So you have an n cross 1 column matrix. That's how you represent it. But notice that this cannot be the fundamental representation. That's not what we are doing here, right? We are not hitting it with an AU. We are not hitting it with a unitary matrix, a U, right? And also the A's live, there are not just one A fields, there are n number of A fields where n is the number of generators, right? So this is what we call the adjoint representation. The A fields live in a whole other representation of the group, and that is why they transform under the gauge in this unusual way. Okay. Now for a unitary group, let's take an SUN group. Okay. How many generators are there? How can we work this out? Let me give you the answer. The number of generators is n square minus 1 for this SUN. Why is that? So when you start out a unit with a matrix, right, it has 2n elements, right? But then you have this condition, correct, for it being unitary. So that would make it 2n would go to n elements in the first place, right? N independent elements, right? And then we have the determinant of u is 1, right? Oh, by the way, I'm sorry, I meant 2n squared. Why n squared? Because it's an n by n matrix, right? And why 2? Because you start out with complex numbers, right? Okay. And then since you set the determinant to 1, that gives you one more constraint, and then you get n square minus 1. Okay. So any unitary matrix can be, this is exactly why any unitary matrix can be written as a combination of n square minus 1 generators. There are n square minus 1 independent elements. Okay, independent, however you want to call it, dimensions or whatever. Okay. Good. Now that would mean the number of gauge bosons is also n square minus 1. can you go back to the first few lectures and think about what this implies for the strong force and the weak force? This tells me that for the weak force, right, which is SU2, I have how many? 2 square minus 1, 3 gauge bosons. What are they called? It's not the W plus W minus and Z. That would come later, okay, after you do the after you do the symmetry breaking, which we will look at. But at this point, you just call them W1, W2, W3. Okay. And similarly, the strong force. How many gluons are there? It is 3 square minus 1, just 8 gluons. Remember, we saw all this in the beginning. This is where it comes from. Okay. To get your gauge invariance, you are forcing the number of gauge bosons to be the number of generators. Okay, excellent. Notice also that with a kinetic term like this, right, where is the kinetic term? So with the kinetic term like this, since I have one field sitting in this with this derivative and with this derivative, and then two of these A fields sitting with this derivative, I can now start getting some very interesting vertices, right. For example, I can have, using my W bosons for instance, I can have a vertex like this. I can also have a 4 boson vertex, correct. That is what we are seeing here, right. 2 of these from one field strength tensor and 2 of them from another field strength tensor. And similarly for gluons, I can have a 3 gluon vertex and a 4 gluon vertex. Remember when we started Feynman diagrams, when we started introducing Feynman diagrams, we saw that these interaction vertices were allowed for gluons and W bosons, but not for the photons. This is exactly where it comes from. The fact that you are now in a non-abelian theory or a Yang-Mills theory is exactly what gives rise to these vertices. Okay. Now, let us look at a bit more about the fundamental and the adjoint representation. Okay. So, I was saying that you can take an SUN, right, which is a set of n by n Hermitian matrices with determinant 1, right. So, let us look at a bit more about what do we mean by fundamental representation, and now what I am going to do is take gauge transformations in the infinitesimal limit. Okay. So, instead of taking the entire U, I am just going to keep terms up to linear order. So, I am going to make use of this, but only up to linear order. Okay. So, what happens then? Let me label the fields I have in my theory with I. Okay. The fields that transform under the SUN. Okay. So, let me write that down right away. Here I runs from 1 to n. So, we are in a sense rotating among these fields, but not real rotation in an SUN space. Okay. So, the infinitesimal transformation should go like this, where I am now changing notation a bit. I'm going to call the generator a generator in the fundamental representation. Okay. See, all I've done now is taken this transformation, written it in linear order, and now I put in these indices. Okay, so here's the transformation, right? So the phi is composed of phi 1, phi 2 up to phi n, right? This capital phi. That's just what I've written down, but up to linear order. Okay? And I can now write down the transformation of the complex conjugate field, and I'm going to write it in a slightly different way. As you would imagine, I still get a minus I alpha. Okay, and if I literally write this, I can put a star here, right, and an A, and it's still an ij phi j star. Okay, but I'm going to rewrite this now. Okay, this is what I'm going to write as phi I star, again a plus I alpha A. I'm going to call this object a generator for the anti-fundamental representation. Okay, what I'm implying here is that I've forced the complex conjugate fields to be in yet another representation that I call an anti-fundamental representation. Okay, so they are living in a whole other representation which is closely related obviously to the fundamental representation. Okay, so what have I made use of here? I can write this because I have made use of the relation this. Okay. Okay, so that should be obvious, right? Not only that, I've also made use of the generators being Hermitian. Okay, so you can go see this. So how do you see this? You see this because the term that I should have written here is not exactly this. Because these are matrices, I should have put the phi j here. Do you agree? In that case, how would the contraction go? It's not a ji, it's not an ij, it is a ji here. Then both these facts would come together and give me this. Okay, so the point I'm trying to show here is that even the generators, they carry information about whether you're in the fundamental representation or not. That is, generators themselves are determined by the representation. So you can see where I'm going with this here. I'm going to wrap up with this concept. If you have the adjoint representation, then they would correspond to their own generators. Okay, the fundamental representation has its own set of generators, anti-fundamental has its own set, but thankfully there's a relation at least between the anti-fundamental and fundamental, and the adjoint representation will come with its own set of generators, and we'll see how that concept becomes important in the next lecture. Okay, all right, I'll see you then. Thank you.